In this video, I'll be explaining the type state pattern. Type states allow you to enforce logic at compile time. Type states leverage the type system to encode state changes. They're implemented by creating a type for each state. The types use move semantics to invalidate a state, and they usually return the next state from the previous state. Optionally, they can also drop the state. Dropping a state is useful for something like closing files or signaling that a resource is no longer available. Type states give you compile time enforcement of logic. This means it is a compiler error if you attempt to utilize logic in the wrong order. Let's take a look at an example. Here we have a bus ticket and a boarded bus ticket structure. The bus ticket will be a ticket that you can use one time, and then once you board the bus, you'll get a boarded bus ticket. So here on our implementation block, we're implementing some functionality on the bus ticket type. We have a board function, which takes a self. We've almost exclusively used a reference to self in most of these cases. However, now we're just doing self with no borrow. This means once the board function is called, the bus ticket will be destroyed. In the body of this function, we just return a boarded bus ticket. To utilize the type state pattern, first we'll create a ticket, which is a bus ticket, and then we'll board the bus by calling ticket.board. Once we call the .board function, we'll get back a boarded bus ticket type, and that'll be saved into the boarded variable. Everything seems pretty straightforward, but here's where the fun starts. If we try to take the ticket and then call .board on it again, we'll actually get a compiler error because the ticket has already been consumed by the board function. So if we try to take one ticket and board 2 times on the bus, then we won't be able to, and the compiler will ensure that it's impossible to occur. Let's take a look at another example. Here we have a struct named file, and the file just takes a string reference, and that will just be like the file path. Here we're implementing the file, and we have a read bytes function and a delete function. The read bytes function will read some data and return it in a vector, and the delete function will delete the file. Notice the read byte function has a borrowed self. The delete function just has self. That means when we call a delete function, this file here will no longer be available for use in the program. So if we look at the code down here, we have a file and we create a new file with data.txt. We then call read bytes on the file to get some data. Immediately after reading the data, we delete the file by calling .delete. Now, later on in the program, this could be 2 lines later, it could be 50 lines later. If we try to read the file again by calling file.readbytes, we're going to get a compiler error. So even though the file variable is actually available, the data is gone, and the compiler will enforce that this happened. So when we call delete, the self was moved into the delete function. So this file was moved into here, and the delete function owns that file. And since delete owns the file, as soon as that function ends, the file information gets deleted. And the compiler again enforces that you cannot read the bytes again because the file was deleted up in here. I'd also like to add that you don't have to include the type state changes within an impl block. They could just be free floating functions. So you could just have a regular function hanging around. You just won't be able to use the self parameter that you normally could. Instead, you'd have to pass in the file itself into the function. To recap, type states leverage the compiler to enforce logic. They can be used for invalidating or consuming states. They can be used for properly transitioning to another state. And they can be used for disallowing access to a missing resource.